Hi, everyone. Everyone's been calling this graveyard shift, but I don't really see it that way because everyone here is either really interested or very enthusiastic to get to the drinks, so you won't ask me difficult questions. I'm James. I'm a data scientist at Landmark Information Group, and today I'll be talking to you about our hex appeal, how we've been optimizing geospatial pipelines using H3 indexing. There you go. So a little bit of background first. So as I said, I'm from Landmark Information Group. We're the UK's largest provider of property data. We provide things like risk modeling for property portfolios and house valuations. Basically, if you've bought a house or insured a house in the UK, you've probably used our services at some point, knowingly or not. Internal to Landmark, I'm part of the innovation team. So we work on all sorts like drawing insights from new and existing data sets, working with generative AI for sort of internal and external products. That's the only time I'll be saying AI in this talk. And what I'll be talking to you about today is optimizing our pipelines. And the use case that I want to talk to you about is GeoCat, or the Geospatial Catalog. So this was a prototype which started basically purely by accident, as all good POCs do, from a question, which was, how far is this from the coast? Now, why do we care about this question? Well, it's quite an important question for a lot of our purposes. Distance from coast influences coastal erosion risk, flood risk, but also can have an impact on house property, both good and bad. So it's quite an important question for us. And the way that we used to find it when I inherited this project was we'd take all the properties in the UK, we'd get the line string for the coastline of the UK, which is actually loads of several line strings because it's very long and complex. And then we would cross-join them all, find the distance for all the properties to all the line strings, and then take the minimum for each one, which, as you can imagine, scales horribly and doesn't actually give you a very good result, as we'll see in a second. So we took this on and we had a look at, well, how can we go about improving this? And in the end, H3 indexing came to the rescue. So why H3? We've probably heard a lot about H3. That's the nice thing about going last, is if I forget to say anything, someone's probably already covered it. So it's got three main benefits. Endless universal traversal. So you can go from hexagons as big as 1,200 kilometers across, all the way down to about 50, in edge length, all the way down to about 50 centimeters edge length, everything in between for the whole globe. They tessellate perfectly, so any neighboring hexagons from a central one will always be a uniform distance, and they tile perfectly. So unlike with squares, there's no sort of routes going on when you're trying to find distances at a diagonal. It's all sort of perfectly distanced. And root 3 is a magic number. So if you take the edge length, which we already know for every resolution, you can very easily find the circumradius. Using that, you can then find the distance between two hexagons, and you can multiply that by the grid distance to get an approximate distance away. So you have very easy mathematics to get approximate distances at any level. And what does this look like when applied to distance to coast? Well, it looks like this. So we found this by taking that line string geometry for the coast, as we saw before, and then doing a K-ring buffer. So essentially, the string of hexagons that follows the coastline, that's 0 distance. Add hexagons out on the outside, that's grid 1. Another layer of hexagons, 2, 3, and all the way out. I think we went to about 15. And then they get colored according to their grid distance from the coast. So you can see it starts out very light as you're further away, and then a much deeper blue when you actually get right onto the coastline. Zooming in, it looks like this. So you can see the old way on the left, you've got all the properties, and then you've got the coastline geometry. On the right, you can see all of those properties have been assigned to an H3 cell, and each of those H3 cells knows roughly how far away it is from the coast, and roughly which piece of line string geometry it's nearest to. And this brought about a bunch of benefits. The first one is that general indexes enable arbitrary searches. So this is a really big issue for us. Obviously, we deal with a lot of property data, and it seems at first glance the best way to store property data is at the property level. But there is that golden rule of data science that the thing that you first think of doing initially is probably the wrong one. So you can look at it like this. If we have a brand new property, doing it the old way, we'd either have to do some sort of aggregation where we take the distances of all the nearby properties and approximate, or we run that really complex process all over again and do a big cross-join for all the line string geometries for that one property. Either way, it's sort of quite complex and not ideal. In the new way, however, that H3 cell already exists. So you can just get the H3 ID for your new property, and you instantly already have an approximate distance to the coast, which might be good enough. If you don't care about properties beyond 2 kilometers, you can just instantly stop. Or you can then calculate the precise distance based on the nearest line string, which you know is there. And that leads me to the second benefit, which is that indexing using H3 reduces computational requirements. So again, going back to how we originally did this, it was a big, horrible cross-join, very complex, and this actually took about 10 days to run for all 40 million properties in the UK and thousands of line string geometries. And as I said, the result isn't ideal. It's not reusable. It's only for that one specific point for each property. Doing it using H3, though, each cell, as I said, already knows which line string it's probably nearest to, based on when we did the K-ring distancing. And that means that rather than for each cell checking the distance to every single piece of line string geometry, many of which will probably be far away or duplicating for neighboring cells, we only have to really check one, maybe two. When you take the whole UK into account doing it this way, 84% of H3 cells only have one nearest line string geometry, and 97% have no more than two. So there might be sort of equidistance from two. But that's still cutting the calculations down by quite a fair chunk. And in fact, as compared to the 10 days with no flexibility, the new way took about 2.5 hours, and then that's for this sort of H3 lookup table, and then for all 40 million properties in the UK, to get an exact distance from the coast, then took about 5 minutes of joining onto that. So quite a considerable increase in efficiency, and it makes it far more reusable, seeing as this data set updates roughly every 6 months. So that's how we can improve both the dataset generation and consumption. If we want to take improving the consumption efficiency one step further, we have another trick up our sleeve with H3, which is the Databricks Mosaic library. And to look at this, I want to step away from the distance to coast for a bit and instead talk about pylons. Now, why do we care about pylons? Well, they have quite a big devaluing effect. There's visual and safety impacts. It has impacts on what you can do with your property if you're too nearby. And we tend to care if you're close to one, but not exactly how close. Unlike distance to coast, where every meter can count, especially with coastal erosion, distance matters for pylons, but not precisely. So if you're within a certain area, for example, a 100-meter buffer, that's good enough to say if it's a risk factor or not. So this is how Databricks Mosaic works, for those of you who haven't seen it before. So we take a 100-meter buffer, for example, around a pylon, and we end up with a bunch of H3 cells. And this central one here, which is more yellow, is called a core cell. And that basically means that that whole H3 cell is entirely compassed by that buffer. Doesn't matter where you are in the cell, you know that you're within that buffer. So if we were to, for example, look at this property, we would know that, okay, well, it falls into this cell. We can do a left join on our H3 lookup table for all the buffers of all the pylons in the UK, and we get a result. There's this cell. Okay, great. Is it core? Is it core? True or false? In this case, it's true, and we can just stop there. So we have left join. We know that it's core. Great. We don't care anymore. It's just that we definitely know this property is definitely within this buffer area. If we were to then look at another property, well, for this cell, that is not core. We can see that it definitely joins onto an H3 cell, which our buffer also includes, but it's not a core cell. It's a chip. And this means that it also comes with chip geometry in the form of well-known byte. And that allows us to do one more stage. So we can do the left join. Okay, great. It's got an H3 match. Is it core? No, it's not. Okay, so then we take the geometry and we can say, do these two intersect, or does this one contain the point? And that just means that we can do a single calculation rather than having to do a contains or intersects calculation for every pylon in the UK for this one property. We already have a very targeted calculation of we only need to do it once because we know it's either going to be this geometry or none at all. In this case, the intersection will come back false, and so we know that this property is not within the 100-meter buffer. And we can sense check that using Kato. And this is a real strength of Databricks Mosaic. It doesn't just come down to proximity and distances. It can come into all sorts of geofencing applications. So for example, how many of these thousands of vehicles fall within this specific area? Or as we maybe saw earlier, how many restaurants are nearby to this user to deliver food to them? That's where Databricks Mosaic really comes into its own. And one more visualization of this. It doesn't even have to be for geofencing or proximity. I really like this visualization because it's quite pleasing to look at. This is for a heat wave, heat stress data set that we have. And the thing with heat waves in the UK is that every county has a different consideration of what counts as a heat wave. They have different thresholds. So we use H3 to speed up the generation of this data set, but we can also use it to speed up the consumption. You can take a property in any cell, we can join onto those H3 cells, and we can say, okay, is it in this one? Great, that's a core. We know which county that's in, job done. Or if it's on the border, rather than having to do an intersect calculation with all of the really squiggly geometry for a county, we only have to do it with this very small amount to know which side of the board you're on. So it can really speed up consumption for a variety of reasons. And that kind of leads me to the third benefit, which is the unification of datasets. So this is a dataset that we got from the Carto Observatory of retail areas around the UK. And you can see here that previously, when we've got datasets from all over the place, they're in all sorts of weird and difficult formats, have to be all aggregated together. You know, they can come from rasters, netcdfs, vector points and polygons and everything. When you index against H3, you can start joining these together in simple SQL one-liners. So there's distance to coast. You can just join that onto the retail areas using H3. Then we've got wind turbines, are you near any of those? Pylons, near any of those? Subsidence scores, which is sort of omnipresent throughout the UK. And so you can really start to simplify down these queries and unify all of your internal data sets, regardless of where they come from, and yeah, generally speed up your sort of customer-facing queries. But it's not just hexagons. As I said earlier, we do deal with a lot of property data, and some of that can't be done in anything other than at the property level. So we have also been indexing using UPRNs, or unique property reference numbers, basically an ID for houses. We used to index everything against UPRN, but as we've seen, that leads to very rigid and inflexible data sets. H3, as we've discussed, is brilliant for distances, aggregations, sort of general data. But because we're British, we also have a nice British grid system. And that's great for UK native data sets. We get a lot of stuff in BNG format, and it's not worth converting it away from BNG because we might start to lose a lot of data quality and detail. You know, if you convert something and it loses 2 or 3 meters, it might not sound like a lot, but when you're seeing if a property is within 10 meters of a house, that really starts to within 10 meters of a tree, that really starts to impact the quality of the product you're delivering. Luckily, though, we have a solution for this. All of these play together really nicely. So we can get UPRN from addresses. They can be converted to either H3 or British National Grid based on lat longitude or eastings and northings. And then they, in turn, can be turned into geometry based on either the mosaic tessellation, or they can go back the other way using the sort of the cell geometry. And that allows all of these data sets, no matter where they come from, no matter what format they're in, to play really nicely. And we are also working on a way internally to be able to translate between H3 and BNG using the grid inquest library available from Ordnance Survey. So that can allow us to make these talk together with a far reduced amount of error. And this is just a sort of visualization of all the different data sets that we've started to pull into this. It's not extensive, not exhaustive. We have lots of other data sets which either have been tessellated in this fashion or can be. And you can see this is just some of the things that we do, you know, risk modeling, valuation. What we do internally does go beyond this as well. But it just gives you an idea of the scope of how applicable this is. Everything from sort of rasters, which are very risk-focused, down to just kind of vector geometry and raster geometry, which is more about value. All of this can be brought together and joined together as easily as we saw earlier with sort of simple SQL one-liners. And then the final benefit is better visualization and improvement for stakeholder engagement. So obviously, as you've seen so far, this is a Carto conference. All of these visuals have been made using Carto. And because it's H3, that plays really nicely with Carto. We can zoom in and out. It's very intuitive to use. And it generally allows for a much prettier looking map. Previously, we've been delivering data at the sort of point level when we've been delivering risk PDFs for all of our clients. It's just been like, you know, a static JPEG or static PNG. It's very unreadable, very unintuitive to look around when there's lots of properties. It basically becomes a meaningless blob of color. But using Carto, we can start indexing at the H3 level, and it's much easier to read. And it even has the sort of ability to zoom in and out, so customers can pan around the data that we've given them and understand it a lot better. And it's not only useful for external use, but also internal. Distance to coast heavily relied on Carto for stakeholder engagement internally and sense checking, so that we could very rapidly update our data on the Databricks side. It would immediately reflect in Carto, and during meetings, we could make changes to some of our processes, update the tables, and then show the reflected changes there and then. And we're really looking forward to working with Carto going forwards. Obviously, as Javier was saying this morning, there's lots of great developments going on. particularly around sort of the AI integrations and the ability to use UDFs, which will really speed up a lot of our processing and allow us to integrate to Kato a lot more. So thank you for listening, and well done for making it to the end of the day. I hope you managed to tick off some of the things from your conference bingo. I know that I probably did a few, and I've definitely seen a few more around the place today. And yeah, if you have any more questions, do let me know. Thank you.